Okay, so the condition for simple harmonic motion is that net force is equal to negative kx. That's the net force on a mass m. So constant mass. And if it's not a constant mass, you don't have simple harmonic motion. You'd still have the equation, you still have the implications. But anyhow, right there is your condition, and then since x being your distance from equilibrium, your displacement should be displacement from equilibrium. So let's go ahead and correct that. Not distance, it's displacement from equilibrium. Then since net force is mass times acceleration, you can write this as mass times acceleration equals negative kx, and x double prime is the acceleration derivative with respect to time. So you have this differential equation that Wes knows how to solve, but you don't. But there's a solution. Okay, x double prime equals negative k over m times x. But I mean, there's the equation reduces to this when you divide by the mass, and then you can verify easily by plugging into the equation that a solution to the equation is x equals some constant, I'll call capital A because we're going to call that amplitude, times the cosine of square root of k over m times t. Now you can verify this by taking two derivatives, and that's very straightforward. And apparently I neglected to write my minus sign there, but now it's a verification because here's your x double prime and here's your x. Okay, and x double prime is the same as x because you got the a cosine square root of k over mt here, but you got a negative k over m out in front, so x double prime is negative k over m times x, and that was the original equation. That's not the only solution. B sine of square root of k over m times t is also a solution, and so is any linear combination of these two. And you can easily, again, verify this. Just take two derivatives of this, and you're going to get negative k over m times this, in the same way we did here. And you want to do that. You want to do that to be sure you understand how the derivatives work and convince yourself that this really is a solution. Now we let omega equal the square root of k over m, and then your general solution could be written as a cosine of omega t plus b sine of omega t, just replacing the square root of k over m by the cosine, by omega. There's another general solution that I'll add right now. And I'll write it in this form. Okay? Now you know that you have formulas for the cosine of the sum of two things, and those formulas come out as cosines, combinations of cosines and sines, and those formulas are easily put into this form. I'm not going to do the arithmetic of that because I believe your web assign will take care of that, or your mastering. So this is equivalent to this. Go back to your trig and rewrite it, and you'll see how these things relate. Now, one thing I've got there that I probably want to change, I've got an a there, cosine of omega t, and this a is not the same as this. So I need to use a different letter there. Okay, so I'll just call it C in this case. It's some multiple of this. Now, that totally matches up with the position of your rider on your beam. Okay? Where omega is just your angular velocity around the circle, if your angle theta is omega t, and that just simply means, well, we know what that means. If this is your angular velocity, you multiply that by your time interval, you get how far you've moved, the angle through which you've moved. So theta equals, if theta equals omega t, then you're at this position. If the circle has radius big A, to match, let's say, the big A you get for the cosine function, then when you're at this position, your displacement from equilibrium, well, here's your x. Okay, that x is just by this triangle, just project this down here, x is a cosine theta, which is a cosine of omega t, which is just this, since the square root of k over m is omega. Similarly, if we wanted to do the y projection, y would be a sine of omega t. Now, as the writer moves around the circle, the x-coordinate goes from here, over to here, and over to here. When you're on the part of the circle close to the x-axis, the writer's motion is mostly in the y direction, so there's not much change in x. When you're near the y-axis, of course, almost all the motion is in the x direction, so now x is changing more rapidly. So x changes slowly as if you're close to this position or this position, and it changes quickly if you're close to this position or this position. That's exactly what a pendulum does. Okay? So this could be a model of a pendulum swinging through, well, in periodic motion with amplitude A. Amplitude being your maximum distance from equilibrium. So there we have that. So I've just made the statement, the motion at this point in the x-axis is identical to that of a simple harmonic oscillator, for which omega is the square root of k over m, and amplitude is A. Okay. Now one thing I want to add here. This is your simple harmonic motion. There's an energy associated with this. And I'm just going to assert it, but you really need to understand it. I say the total energy is, I should have said the total energy relative to the equilibrium position. That's too small to read. Energy, but I've qualified it, so I can't be sued. Relative to the equilibrium position, total energy is the integral from 0 to your extreme position of your force. And that's actually equal and opposite to the force. So I'll say this. Your maximum potential energy is the integral of kx dx from 0 to a, which is 1/2 k a squared. Okay, this is the work you have to do to move the oscillator from equilibrium out to position A. It's equal and opposite to the work done by the conservative force, which would be the integral of negative kx dx. Being equal and opposite, it would be negative the integral of negative kx dx, which is the integral of kx dx. That's your maximum potential energy. At any point, you could calculate the potential energy, and it would just be the integral from 0 to x of kx dx. potential energy as a function of x is the integral from 0 to x of kx dx. And I should use a dummy variable in here. But I should have used some other variable rather than x inside here. But anyhow, it's 1/2 kx squared. Well, if your maximum potential energy is this, the force is conservative, so your total energy is equal to this. Now you can prove this is a conservative force very easily. It's path independent. It doesn't matter whether you're moving from equilibrium out to this position or from this position back to equilibrium, and that force is still negative kx. So that's a path independent force, meaning that energy is conserved, so your maximum potential energy is your total energy. And your potential energy at position x is this. So what's your kinetic energy at position x? Kinetic energy is your total energy minus your potential energy, which is going to be 1/2 Ka squared minus 1/2 Kx squared. So, right here's your energy picture for a simple harmonic oscillator. That's all there is to it. Now this...
I'm pointing that camera down just a touch.
Yep. So let me say it again while I'm pointing at it. Total energy relative to equilibrium is equal and opposite to the work done by the conservative force, which turns out to be the integral from 0 to a of kx dx. It's an integral you should be very familiar with at this point of the course. I believe your mastering physics has fully prepared you to understand this. If not, make sure you review it. So it's 1/2 Ka squared, your total energy. This is a conservative force. It's path independent. When you're at x, it doesn't matter whether you're moving that way or this way. That's your force. So that your total energy is equal to your maximum potential energy. Your potential energy at position x is just the same integral from 0 to x rather than 0 to a. It's 1/2 kx squared, which implies that your kinetic energy is the difference, being the difference between your potential energy and your total energy, is 1/2 Ka squared minus 1/2 Kx squared, which is, of course, 1/2 K times the quantity a squared minus x squared. Don't really have room to write it, but it's probably... Hopefully that's legible. Okay? All this can be related back to here. I don't have room to do it on the board, but you can easily enough, if you have this function, calculate everything based on your kinetic energy. Okay, so your maximum kinetic energy occurs when the cosine of omega t is 1, when x equals a, and that kinetic energy is x prime. So maybe I do have room to go ahead and obliterate, well, just confuse the issue a little bit. X prime equals negative omega a, unnecessary parenthesis there, but we'll live with it, times the sine of omega t. So your maximum kinetic energy occurs when the magnitude of the sine is 1, because the sign goes from -1 to 1. The maximum absolute value of the sign is 1. This is your velocity. Your maximum kinetic energy is ½ your mass times your maximum velocity squared. Don't have room to write out everything I'd like to write. That's 1/2 the mass times we'll just say omega squared A squared. And this equals your total energy. Now, mass and omega and A are related by these quantities over here. And I don't have room to make all the connections, but if you substitute the right quantities over here into this, you can change this to 1/2 K A squared. You got the A squared here. Omega squared is K over M. So M omega squared is Ka. Km is omega squared is K over M. The M's divide out, and you have 1/2 Ka squared. Okay. I'm not going to do that. I believe your book will do that, but I really don't have room to write it any place coherent. Maybe I'll just write a little. Omega squared is K over M. If you plug that in, you get this. So it all works. And then your kinetic energy at any point is 1/2 K x squared, because x is a cosine theta, and you have cosine squared plus sine squared equals 1, and all that stuff. So with just a little manipulation, we totally resolve this picture with not only these relationships here, these formulas if you like, I don't like that word, and with the energy picture. So this is kind of a big deal, worth understanding. And hopefully we can pull this together when we actually get into the detailed study of simple harmonic motion. I would recommend reviewing everything that I just showed you here, and try to have it sort of in your head to give you an overall picture of what's going on with simple harmonic motion before you dive into the text. So you got a simple 15-minute video here that I think gives you a pretty good overview, even if you don't understand every detail of it. And if you do, you're probably not going to have much trouble with simple harmonic motion.